Good day, everyone. In this session, we will discuss about X-ray crystallography, the technique which has helped us understand how a crystal is looking like, how the atomic or the molecular nature of the crystal and the nature of chemical bonds within a crystal, and how exactly the structure of molecules can be deduced by looking at the specific patterns that they make when they interact with waves or the rays like the X-rays. So what you're seeing right here on the screen is X-ray diffraction patterns. The left hand side that you're seeing is one of the early X-ray diffraction patterns which was taken, and the on the right hand side you're seeing a modern X-ray diffraction projection. So what you're seeing here is the dark spots on a white background or an illuminated spots on a background. So what does these spots speak to us? What are the information that we can deduce or infer from these spots? That is what we are going to look at today. And how exactly does this happen? And what are the phenomenon that is working, which help us understand the arrangement of atoms within a crystal, and what are the volumes of information that we can get from just looking at the arrangement of the atoms within a crystal. Moving on, what is the major importance of a crystal? Crystal, as you all know, is a unique structural arrangement of atoms or molecules in space, and it is this crystalline nature of molecules which help us understand how the atoms work together when they are in a system. So it is a near perfect repeating arrangement of molecules in a solid state, and these repeating units in the crystal is known as a unit cell. So crystal is basically built up of billions of such unit cells packed together with each other, giving rise to a three-dimensional structure. We are all familiar with crystals, starting from the table salt that we use every day, the sugar molecules, the snowflakes, the diamonds, and the protein molecules are one of the major important life molecules. So how exactly is this crystal or the study of the crystal structure becoming very important? We all know in case of proteins, the structure of the protein influences greatly its function. So we understand that when there is a change in structure, there could probably a change in the function. And sometimes this little change in the structure could ultimately result in a drastic change in the function, which can sometimes be lethal as well. So that is why the study of crystals is becoming very important. So why exactly do we need to have a crystal in the first place for this kind of study is because when these are in precise positions, each atom or molecule can only be determined if the molecule is crystallized, because in a non-crystallized form, what happens is X-rays will diffract in an unpredictable manner, which we cannot identify, and we will not get enough of data to understand how the atoms interact with each other, what are the kind of bonds that they share between each other, and what kind of structure they could be forming when they interact with each other. So such informations are made possible only when the molecules are in a crystallized form, because when an X-ray or any kind of such rays falls on this kind of crystal molecules, they diffract in a definite manner, and that will give us a definite pattern which could be related as a fingerprint of that particular pattern, particular material. So that is the significance of the crystal. So how did all of this came into action, or how is this mechanism made possible. It all started with an accidental discovery by a German physicist, William Röntgen. He was studying gases in his laboratory when he observed that some photographic plates near his equipment was glowing. So looking at what is making these photographic plates glow, he sensed that it is because of some kind of radiation that is getting emitted. And since he did not know what kind of radiation it is, he just named it as X radiation, X standing for the unknown in maths. So, with the use of this X radiation, what he did was he pictured his wife Anna's left hand. And the picture that you're seeing right here is the very first world's human X-ray to be ever taken. And this X-ray has changed the face of medical diagnosis. And the comment that came from William Röntgen was, "The doctor will now see through you." So, and it is this discovery that has helped him gain the prestigious Nobel Prize in Physics in 1901. So, what are X-rays? They are a part of the electromagnetic radiation. As you can see here, it is a short wavelength light, which is shorter than the visible light, and it is extremely useful when examining materials that are too small to observe with regular microscope. And since when this X-ray falls on matter, it produces certain kind of patterns which are unique to that particular material, and that pattern is known as the X-ray diffraction pattern. Using this X-ray diffraction pattern, crystallographers can analyze or to determine the arrangement of atoms within a particular crystal. So it is the X-ray diffraction patterns that has revolutionized the way people look at material, and the crystallographers can understand the way in which the atoms are arranged within a crystal. So what is diffraction? Diffraction is nothing but a phenomenon that occurs when waves such as X-rays hit an obstacle. Diffraction, as you can see here, when the X-ray particles or a beam of wave falls on a material, in this case a crystal, the beam will get diffracted, so or it gets scattered, and here this is elastic scattering. In this particular type of scattering, where the wave interacts with a particle, it bounces off in some direction, but there will be no change in the wavelength. And this, when it falls on a film, it will give you some specific patterns which we call as the X-ray diffraction pattern. And using this X-ray diffraction pattern, the crystallographers can identify the three-dimensional structure of molecules, how the atoms are arranged within a molecule, which ultimately helps us to determine the 3D structure of a molecule, the crystal. So this X-ray diffraction has been used in analysis as a technique we call as X-ray diffraction analysis technique for understanding materials to determine the crystallographic nature of a material. X-ray diffraction analysis works by irradiating a material with an incident X-ray, and then by measuring the intensities, the scattering angles of the X-ray that leave the material, we can deduce or identify the structure of that particular particle. And this is a primary objective, or the use of X-ray diffraction analysis is the identification of materials based on the diffraction pattern. So it helps us also understand if there is any internal stress or a defect which could lead to the structural deviations that can also be identified by using X-ray diffraction patterns. So in case of the proteins, we can also study the conformational changes that could lead to the change in structure of a particular molecule. So how does this X-ray diffraction analysis work? This is all based on a law put forward by Bragg and Bragg, that is Sir William Henry Bragg and Sir Lawrence Bragg, which later came to be known as the Bragg's equation or the Bragg's law. So in 1912, 1913, Sir William Henry Bragg and his son, Sir Lawrence Bragg, achieved in giving rise to what we know today as X-ray crystallography, mainly based on this principle of X-ray diffraction. And for their work, they were awarded Nobel Prize in 1917 in physics. And this tool has revolutionized the study of the shape and arrangement of molecules within a crystal. And this technique has now helped us bridge the gap between physics, chemistry, and biology, and it has now helped us in solving the three-dimensional structure of complex molecules, life molecules like proteins, the vitamins, the nucleic acids. And it has turned out to be one of the major technique in the field of material characterization, which gives us information about the crystalline as well as the amorphous nature at the atomic level. So here you can see the Bragg's equation, how the which relates the definite relationship between the angle at which a beam of X-ray falls on a particular plane of atom in a crystal, and what is the kind of reflection that it is giving us, and how exactly this ultimately result in the formation of a particular diffraction pattern, which we could even call as a fingerprint of that particular molecule. So the Bragg's equation states that 2d sine theta is equal to n lambda, where n is any integer, lambda is the wavelength of the incident beam, and d is the spacing between, as you can see here, spacing between the diffracting planes, or the lattice spacing between the crystals, and then the theta is the angle, incident angle of the beam. Okay, and lambda is a wavelength. So this law specifically relates the wavelength of electromagnetic radiation to the diffraction angle and the lattice spacing in a crystal sample. So it gives us an idea of how an X-ray, when it hits a crystalline molecule, behaves, and what is the kind of pattern it will generate once the diffraction is taking place, or the interaction between the X-rays and the matter. So this particularly happens like diffraction, and it is also the result of certain another kind of phenomenon known as scattering and interference. So when an incident X-ray beam hits a scatterer, or in our case a crystal or a molecule that we are trying to learn about, the scattered X-rays are emitted in all the directions. Sometimes what happens is they can interact with each other. That means the different kinds of waves that come out, the scattered wave that come out, can interact with each other in such a way that they are out of phase, and they are destructive, or they make each other neutral. For example, you can see here in the picture you have a wave and a trough. So these two can cancel the effect of each other, but at the same time, in constructive interference, the behavior of the waves can be kind of constructive kind, and they complement each other, and by that we can have or we can deduce the relative positions of the points, which are related mathematically to the crystal unit cells in a particular uh, matter that we are trying to understand. So this also, or the crystal in the repeating units in a crystal, can act as a diffraction grating, and thereby they can effect constructive interference, which ultimately result in a particular pattern that is being formed by the interaction between the X-ray and the molecules. So that is what helps us identify the structure of that particular crystal. So how does this work? The X-ray diffraction technique is mainly based on the constructive interference of a single wavelength of X-ray, the monochromatic wave X-ray, and the sample that we are trying to learn about. So we will have a source of X-ray, usually a cathode ray tube, which will be producing the X-rays, and with the help of some optics, we can have this monochromatic grating, which helps us filter out the rays with only a single wavelength. And using a collimator, these single wavelength of X-rays or the monochromatic rays can be made to fall on the sample that is held in position. And once this X-rays hit on this sample, the rays will get scattered. And this scattering, in our case, which result in constructive interference, when it falls on the detector or the film, it will give you what is it, a definite pattern. And with that pattern, we will be identifying all kinds of matter ranging from fluids to powders and crystals, and understand how the molecules are arranged within this crystal. And this X-ray diffraction analysis is considered to be one of the most important non-destructive instruments which help us analyze the 3D structure of molecules. The most important or unique method for determining the crystallinity or the crystalline nature of different compounds is X-ray diffraction analysis. So from research to fabrication and engineering, X-ray diffraction analysis has now become an indispensable tool for not only studying the material characterization, it also helps in quality control, in trying to understand the purity or nature of particular compounds. It helps in the identification of the crystalline material and identification of the polymorphic forms. That means each material will have its own chemical fingerprint, and then distinguishment between the amorphous and the crystalline nature of a material, then the quantification of percentage crystallinity of the samples, the purity of the samples. All these can be achieved using the X-ray diffraction techniques. That means, in effect, each material will have its own unique X-ray diffraction pattern, and these patterns can be called as fingerprints. And if you are having an unknown material you want to study, what you can do is go for X-ray diffraction pattern study analysis, take the X-ray diffraction pattern, which is considered to be the chemical friend of that particular compound, then compare this diffraction pattern with a database of known patterns, and then you can deduce or find out what exactly is your sample. So that is the importance of X-ray diffraction analysis. And all these came into play because of the findings by William Röntgen, the X-ray. And how exactly this X-ray diffraction pattern has revolutionized the way we look at biological science today is because this X-ray diffraction analysis helps us understand the life molecules like the proteins and the nucleic acids. And what you're seeing right here is the picture of Rosalind Franklin along with her X-ray diffraction pattern of the life molecule DNA, which has revolutionized or which has helped us understand how this genetic material is and what it is made up of and what is the structure of the molecule. And we all know the structure is related to the function. So it is with the help of this X-ray diffraction pattern of DNA by Rosalind Franklin, James Watson and Francis Crick got the evidence to prove that DNA molecule is a double helical structure. And this X-ray photograph came to be known as photo 51, and it is one of the diffraction patterns that helped us understand the true nature of the biological molecule DNA. And interestingly, there is a small read from the Double Helix, the book written by Watson, in which he has mentioned how excited he was in seeing this X-ray diffraction pattern by Rosalind Franklin of the DNA molecule, which clearly depicted the double helical nature, not just the double helical nature, but also how the molecules are arranged within the double helix, the distance between each turns, the nucleotides, etc. And what he wrote was, The instant I saw the picture, my mouth fell open and my pulse began to race. The black cross of reflections which dominated the picture could only arise from a helical structure. And it is this diffraction pattern that became the solid evidence to prove that DNA is a double helical structure, and it is with this evidence that Watson and Crick proved that DNA is a double helix. They were awarded Nobel Prize for their discovery of the double helix, which they shared with Maurice Wilkins. But in the whole story, unfortunately, Rosalind Franklin was never recognized for her studies, and she was not part of the Nobel Prize. As all know, she died at a very young age, and Nobel Prize is never awarded posthumously. So that is the story of how X-ray diffraction pattern has revolutionized the way in which we look at biomolecules today. And this is her famous picture, which came to be known as Photo 51. So, with that classical example of how X ray diffraction could help us reveal the nature of molecules, the whole area of X ray crystallography came into being. And this is a method of determining the arrangement of atoms within a crystal. And this is a non destructive technique, as I already told, which is based on the X ray diffraction patterns, which are unique to a particular molecule, which we can call as the fingerprints. So, what is the basis? What is the basic principle behind this? We all know that when a beam of X ray strikes a crystal, the beam gets diffracted, constructive interference. What happens? It can lead to a diffraction pattern. So, from the angles and the intensities of the diffracted beam, a three-dimensional picture of the density of electrons within the crystal can be derived at. And from this electron density, the mean position of the atoms in a particular crystal can be determined. And this works as an atomic microscope where we are using X-rays instead of visible light to determine the three-dimensional structure of crystals. So this is the whole arrangement of X-ray crystallography. You have an X-ray tube, then filter which will filter the X-ray beam, and the monochromatic rays falls on the crystal, and then from there it gets scattered. Constructive interference, you have your photographic plate which takes up all the patterns, and by analyzing, by using computational methods, we can reduce a pattern, we can read the pattern and come to a conclusive nature where we can have the three-dimensional structure of the whole matter. So this is again the principle. This picture shows the principle of X-ray crystallography, and the underlying principle, as I already told, is that the atoms in a crystal can cause a beam of X-ray to diffract in specific directions, and by looking at the angle and the intensity of the diffracted beam, the crystallographer produces a 3D structure of the density of electrons within the crystal. So this not only helps us deduce a 3D structure of the material, it also helps us in understanding the different types of chemical bonds that is there existing within the atoms or between the atoms in a crystal, then their order in which they are arranged. So if we can understand the order, we could definitely see the disorder also when there is any change in the conformational states of the matter. So this has become one of the most indispensable tool in understanding the nature of biomolecules, and it has, as I said earlier, bridged the gap between physics, chemistry, and biology. So this is in a nutshell the workflow of solving the molecular structure of a molecule using X-ray crystallography. The first step is whatever the sample that you are trying to study using the X-ray crystallography, you need to first crystallize. There are up to a number of ways of crystallizing molecules. So once you have a successful crystal, you can now put it subjected to X-ray radiation. So once X-rays falls on it, it will diffract and it will produce a pattern in a photographic film. And based on the different phases, we can look at the electron density map that it is creating once the X-rays hits the crystals, and primary models can be formed. the structure of the atomic models can be made, and at different angles we can have the diffraction patterns, and by looking at the different ways in which the atoms are arranged, the electron density map at different angles, you can form atomic models and validate and refine these models until you get the same diffraction pattern of a known particular pure compound. And that is how, with the computational methods, we come to the structure of that particular compound. So this is very, very significant as far as drug development industry is concerned, where we are using the structure based drug designing. So X-ray crystallography has become one of the most trustworthy techniques which can be adopted for designing drugs based on the structure, because structure is very much important, because how molecules interact with each other, especially in pharmaceuticals, how the drug molecule interacts with the target molecule, it's all dependent on the structure of both. So this in a nutshell shows the process of resolution of molecular and crystallar structure of by the X-ray diffraction. You have the purification of the compound. Once the compound is purified, you go for crystallization, then go for X-ray diffraction. You have your pattern. You can go for data processing with the help of computational systems and programs, and from there you can learn about the electron density, and you can have your atomic models. So this is model building. So you go for refinement of the model, looking at the density, electron density of the molecules or the atoms at different angles, and then you go for validation, and finally you will have your atomic model ready. So refining the model, adjusting all the atomic positions to get the calculated diffraction pattern, which is as similar as possible to the experimental diffraction pattern, will help us finally validate and come to the total structural model of that particular compound. So, as I said, the structure is very much important and very much related to the function of particularly the proteins. So, we need to have an understanding of the pattern to get the lattice parameters of the unit cells, the symmetry, as well as the diffraction intensities to understand the chemical nature, the bond nature, and how the molecules interact with each other. So, speaking about the applications, we have already been saying it helps us understand the structure. It helps us understand the size of the atoms, the length and type of the chemical bonds, the atomic scale differences among the various materials, then about the crystalline nature, the crystalline integrity, how the grains are oriented within the crystal, the size of the grains, the thickness of the film, interference roughness of the related materials, especially the case of minerals and alloys. These becomes very important. In biology, the this X-ray crystallography will reveal the structure and function, and thereby the function of many of the biomolecules like the vitamins, the drugs, the proteins, and the nucleic acids. So this has become a very important tool as far as protein structure and function study is concerned, that is in the field of proteomics. So this is just to show you how the X-ray crystallography is applied in various fields. The first one that you are seeing is the molecular structure of the pneumococcal surface enzyme, and how exactly the crystalline nature is used to deduce the structure, the active positions, and how molecules interact with each other. If you take a look at this, the rotating molecule, you can see how we add on the molecules and the atoms to come to a final structure, the final modeling of that protein. And the second picture shows how exactly the unit cells are being packed within a crystal, that is a molecular packing of a simple organic compound. And this shows how it looks like the unit cells in a crystallographic nature. And the last one shows how molecules interact with each other and the fragment of molecular structure of a protein, because we know the drugs and the target proteins, how they interact with each other is very much important to know the efficacy of a particular drug to maybe prevent a disease or to cure a disease. So X-ray crystal structures can also explain the unusual electronic as well as the elastic property of materials, and it also helps to shed light on the chemical interaction and processes as we have discussed right now, then function on the basis as a basis for designing pharmaceutical against diseases, which I said, structure-based drug designing. So this is also employed routinely in determining how pharmaceutical drugs interact with its protein target. And by understanding this kind of interactions, we will know how exactly to modify the drugs in order to make it more efficient. As I said, so very much used in proteomics, determining the structure of proteins. What you're seeing here is a capsid structure of different types of viruses. The first one is a poliovirus, and second is a hepatitis B virus capsid. And by looking at all these, we can also make the drugs to counteract these viral proteins or the viral toxins. And then you can also learn about the interaction between molecules, and that helps us in understanding the function of proteins. This is how the structure formation helps us in understanding the active sites of proteins, major amino acids, where they are present and how they will interact with each other. And then again, it speaks volumes about the conformational states of the proteins and the spatial arrangement of atoms in a molecule that can come about because of the free rotations of atoms about a chemical bond. And it is necessary to determine the arrangement because it helps us understand the structure and thereby function of a protein. So all these is very important, and this is yet another example where this X-ray crystallography comes into play when it helps us determine the catalytic property or efficacy of certain enzymes. Enzymes, we all know, are catalysts in many of the metabolic processes or biochemical reactions that is taking place within our living system. And the determination of the structure and type of amino acids present in the active sites truly determines how the catalytic activity take place and the interaction level of enzymes with its target molecules. And this again helps us predict how efficiently an enzyme will have its catalytic activity given a particular situation. So these are all some of the major applications of X-ray crystallography in various areas of research as well as development. Why this has become such an important tool in the study of materials is because it has got certain advantages. The most important being that it helps us investigate the micromaterials as well as the macromaterials, and altogether it is a non-destructive mechanism which causes no damage to the samples since we are not using much of the harmful rays or the chemicals. It is free of pollution, and it is low on environmental requirements. Then it's high performance and precision over many of the other such mechanisms makes it a wonderful tool which can be relied upon. So coming on to the key points to remember, X-ray crystallography is an essential technique which is a form of very high resolution microscopy which works on the X-ray diffraction pattern based on Bragg's equation, and it helps us visualize the way atoms or the unit cells are arranged within a crystal. Especially, it helps us identify how the biomolecules are constructed, how exactly the structure of the biomolecules, especially the protein structures at the atomic level, which help us understand the function of the biomolecules. Then it also gives us details about the type of chemical bonds, the nature of the chemical bonds, how molecules interact with each other, which helps us understand if there are any deformities or conformational changes which could ultimately affect the function of that particular molecule. For example, we just saw about the catalytic nature of enzymes. So armed with these informations, we can develop novel drugs specific targets, specific novel drugs, which can help us combat many of the diseases. And it is not just in the medical field that this is important, it is also important in engineering as well as material science and also in specific industrial processes. So, this is all about how X-rays, X-ray diffraction, and X-ray crystallography help us understand the biomolecules in detail. Thank you for your patient listening.